An important concept in physics is the idea of conserved quantities. These are certain physical quantities that are conserved in nature. That is, the total amount of it never changes in the universe, but it can move from one object to another or change form. One of these is mass/energy. We'll consider only the energy aspect of this. Energy can take a number of forms: kinetic energy, potential energy, heat, light, and it can be exchanged from one object to another. For example, when you heat water on the stove, electrical energy is being turned into thermal energy. But the total amount of energy in the universe never changes. The other conserved quantity that we'll see today is momentum. The momentum of an object is its mass times its velocity. When objects collide, momentum can be exchanged, but the total amount of it doesn't change. The third conserved quantity that you'll study later on is angular momentum. Another conserved quantity that's familiar to you is electric charge. Protons have positive electric charge and electrons have negative electric charge. When a proton comes into being during a nuclear process, so does an electron, so that the total electric charge in the universe is unchanged. There are a few other conserved quantities related to more complicated and esoteric physics. Together, these conserved quantities are a major part of physicists' understanding of the dynamics of nature. This lab investigates the conservation of energy and momentum. Here's the ballistic pendulum simulation. If I fire the bullet, it embeds itself into the block, and the block starts to swing. And of course, the faster the bullet is going, the higher the block will swing. We're going to measure how high the block swings, and from that information we'll use the conservation of energy and momentum to calculate how fast the bullet was going before it hit the block. So let's reset the simulation, and I'm going to set this measuring line at the vertical position of the bullet when it starts. So it starts at a height of 1 meter above the floor of the lab. Now I fire the bullet and the block swings. I want to find out how high the block swings, so I'm going to try to pause the simulation right when the block reaches its maximum swing height. So now let's reset the measuring line to see how far up the bullet and block have swung. And it looks like they've gone up to about 1.43 meters. That means they have been raised 0.43 meters since they started at 1 meter. Raising up an object takes energy. The amount of energy required to raise an object to a height h is P equal mgh, the mass of the object, times g, the acceleration due to gravity, times the height. P stands for potential energy because you put this much potential energy into the object when you raise it up. The masses of the bullet and block we'll call little m and big M. So the potential energy put into the bullet and block is given by this expression. So where did this energy come from? The answer is that it came from the kinetic energy that the bullet and block had just after the bullet embedded itself into the block. This kinetic energy is given by 1/2 times the total mass times their velocity squared. So the PE came from KE, which means that PE equal KE. Now we have an expression relating the height that the block swung up to the speed that the bullet and block had after the bullet embedded itself into the block. But what we want to find is the speed of the bullet before it hit the block. For this we'll use conservation of momentum. The momentum of the bullet before hitting the block is its mass times its speed. And the speed of the bullet and block after impact is the total mass times the speed. Since momentum is conserved, these two are equal, and now we have an expression connecting the speed of the block before hitting to the speed of the block afterward. So the idea is that you'll use the energy conservation equation to relate h, the height that the block rises, to v2, the speed of the bullet and block after the bullet impact. And then you'll use the momentum conservation equation to relate v2 to v1, the speed of the bullet before impact. One more point to make. We used energy conservation for the second half of the process and momentum conservation for the first half. But aren't both of these quantities conserved all the time? Can't we use energy conservation to relate v2 to v1? The answer is yes, energy is conserved during the bullet impact, but it doesn't all remain kinetic energy. Most of the bullet's energy turns to heat as friction stops it when it enters the block. So if you could carefully measure the thermal energy, then yes, you could use energy conservation in that part, but that would be a much more difficult experiment. Similar problems hold for using momentum conservation during the second part of the process.